Welcome to This Explainer. I'm absolutely thrilled to be your guide today. We're going to explore something truly fascinating, how ancient cultural traditions are literally being quantified and analyzed using modern technology. It's this brilliant intersection where the subjective past meets the cold, hard empirical present.
So, let's dive right in by asking a question that bridges two completely different worlds, right? The subjective, sensory experience of our ancestors versus the cold, empirical data of today. For decades, we've kind of treated cultural heritage as something to just, observe or preserve behind glass in a museum. But what if the traditions of the past hold complex scientific data just waiting to be decoded? How exactly do we translate indigenous practices into hard science?
Here is our roadmap for today. We'll be covering the Ethno-STEM paradigm, vernacular architecture design, herbal tea aroma extraction, IoT and sensor arrays, identifying volatile compounds, and finally, fostering global diversity.
All right, let's kick things off with Section 1. The Ethno-STEM paradigm.
The absolutely crucial point here is that this isn't just about preserving culture for history's sake. No, it's a highly innovative educational framework called the Ethno-STEM Integrated Inquiry-Based Project Learning Model, or a bit easier to say, IBPJLM. Think of it as a transformative pedagogical tool. It takes indigenous knowledge, stuff communities have known for generations, and reconstructs it directly into formal, rigorous scientific knowledge. It literally merges cultural heritage with advanced engineering and STEM principles.
Moving on to Section 2, Vernacular Architecture Design. So, according to recent research by Haryanto and colleagues in 2024, students are actually applying principles of structural engineering, geometry, and physics by designing and building miniature models of traditional Gadang, Kadidiang, and Kambuk houses. Now, instead of just admiring their aesthetic heritage, which is beautiful obviously, these students are drastically improving their numeracy literacy and spatial reasoning. They're actually analyzing flat building materials and calculating structural loads, all while carefully maintaining the cultural and aesthetic integrity of indigenous architecture. It's basically pure physics disguised as cultural art. That brings us to Section 3, Herbal Tea Aroma Extraction.
Now check out this highly innovative project led by Sudarman and colleagues. It brilliantly maps the intersection where the traditional Indonesian ngeteh, or tea-drinking culture, perfectly merges with modern inquiry-based learning. In traditional culture, tea is totally recognized as a local wisdom practice. You know the drill. You brew the leaves, a distinctive aroma is released, it calms the mind, and provides health benefits. But with this project, we aren't just stopping at, hey, this feels good.
Here we narratively pivot from those sensory experiences, like inhaling a calming vapor for wellness, straight into the empirical science. Through this framework, students are translating these indigenous practices into hard science. They analyze how traditional boiling and brewing are in actuality the formal scientific processes of maceration and extraction. The traditional knowledge of inhaling tea vapor for wellness is scientifically deconstructed. Why? To prove that young tea leaves are rich in bioactive secondary metabolites, specifically polyphenolic compounds, tannins, and volatile essential oils that actively influence human focus and fitness. It's pretty amazing.
Let's look at how they measure this in Section 4, IoT and sensor arrays.
Okay, let's dive into this awesome Frankenstein tech. To physically capture and identify the chemical signatures of various herbal teas, including some sourced from the communing tea plantation and tropical forest plants, students engineered this volatile compound tracer tool. They literally took an everyday coffee maker, which functions as a thermal bath to heat the samples, and retrofitted the lid with an Arduino ATmega 328 microcontroller connected to a breadboard. They integrated Internet of Things capabilities right into a standard kitchen appliance. Talk about inventive.
So here's how the data extraction procedure works in the lab phase. Students brew exactly 5 grams of powdered tea in 100 milliliters of water inside this modified coffee maker. As the tea evaporates, the compounds are aerosolized using a nebulizer. Then, the sensors trap that concentrated gas vapor. And what happens next is pure magic. The sensors convert the chemical concentration of those volatile compounds into continuous electrical signals. These readings are captured at rapid intervals, just 0.5 to 1 second, for a precise duration of 2 minutes. This ensures a completely stable, accurate profile of the aroma. Just look at the sheer specificity of the sensor array they mounted to that Arduino. These modules are meticulously calibrated. The MQ9 targets carbon monoxide. The MQ135 hunts for ammonia and alcohol. Meanwhile, the TGS 2602 and 2620 modules are tasked with identifying pungent, volatile organic compounds, organic solvent vapors, and acetone. It gives us this unprecedented ability to track distinct classes of volatile molecules in real time as they literally rise off the tea.
Which leads us right into Section 5, identifying volatile compounds.
So once those rapid electrical signals are processed through the Arduino IDE software and exported to Excel, we transform a subjective, calming aroma into exact, quantifiable parts per million data. Here we have the visual proof. It shows that Arduino gas sensor technology successfully bridges traditional sensory experiences with real, quantifiable chemistry. When the students analyzed the exported data, they identified a remarkably complex profile of volatile organic compounds that make up the aromas of these herbal teas. We are talking exact measurements of carbon monoxide, carbon dioxide, ammonia, ethanol, acetone, propane, LPG, and various complex esters. By doing this, we've successfully deconstructed traditional wisdom to prove mathematically what indigenous cultures have always known. These young tea leaves are actively rich in volatile, essential oils that have tangible, measurable impacts on the human body.
Finally, Section 6, Fostering Global Diversity.
Ultimately, this whole project serves as a deeply transformative pedagogical tool. By engaging in ethnotechnology and ethnoengineering, whether that's analyzing the structural loads of traditional ngeteh architecture or engineering an Arduino sensor to track ammonia in a local beverage, students are actively applying science. They drastically improve their 21st century critical thinking, their spatial reasoning, and their overall scientific literacy. They aren't just memorizing textbooks, they are engineering real solutions to measure the world around them. And you know, validating ancient traditions with modern science built a deep, lifelong respect for local heritage. The research emphasizes that this Ethno-STEM approach fosters what they call a global diversity character. Think about it. When students prove with their own homemade sensors that their ancestors' architectural designs were structurally sound, or that their traditional teas are genuinely rich in complex beneficial compounds, it instills a profound conservation mindset. They learn to value and protect their cultural identity because they have validated its worth through the absolute rigors of modern scientific proof. I'm going to leave you with this final, provocative thought. Look around your own home, your own family history, or your local community. What ancient tradition, family recipe, or generational practice is just waiting to be translated into hard science? Heritage isn't just history, guys. Sometimes it's just science waiting for the right sensor. Thank you so much for joining me on this explainer. Keep asking questions and keep exploring.